So we're going to continue our work on this problem, and with this video we should finish it. And just to refresh your memory, although you're probably coming straight from the other video, we had just simplified our expression down to the following. We had 0 equals this big expression here on the right hand side. And remember what you're doing when you're employing this, which is called the method of Frobenius, is you're trying to find two series solutions to the differential equation that you started with. And also, when you're looking at the method, you're told in the big theorem in this section, which is on page 249, that you can come up with your series where the number r is some constant to be determined. The thing that determines that constant is actually this equation that we landed at here. So here's the deal. If this thing is going to equal 0, here we were working at the ordinary point, or sorry, not the ordinary point. This is a regular singular point. Regular singular point for us was x equal to 0. So we're never actually going to use 0 as the x. So this can't be 0. This can't be 0. This can't be 0. So if this sum is going to equal 0, then this guy has to be 0, and this has to be 0 for each and every value of k. So the first creature here is called the indicial equation. So we have r times 2r minus 1 c naught equals 0. And it was a while ago, but remember, we assumed that c naught was not 0. So that tells you that r times 2r minus 1 has to be 0. And this gives you your two values of r. So here r can be 0 or r can be 1/2. Okay, so again, indicial equation. This other pink piece here gives you your recurrence relation for the coefficients. So we're going to need this big expression equal to 0, which I can doop doop diddy diddy, I can sing to you. So that's what we want to happen. And if that's going to happen, then that means that we can solve this for c sub k plus 1. Again, really got to pay a lot of attention to what you're doing on these problems, because you can drop a constant or a coefficient so easily. Just write something down wrong and then the whole problem's wrong, and it can be very hard to find where you did that mistake. So you've really got to do these very carefully, very slowly, really get sort of OCD about what you're doing. Okay, so you have your indicial equation here. That's the guy with the r's. And here's your recurrence relation between the coefficients, so that you can determine the next coefficient once you know the one before it. And that's your recurrence relation. A lot of times in the problems, I'll simply ask you for these two things and then stop, because going forward from here is not hard, but it's just a little bit annoying. So here's what you do. To get your actual series solutions, you're going to take each of those r values one at a time, and you're going to work with it. So if r equals, let's go ahead and do 1/2 first. then the recurrence relation becomes this, which you can clean up a little bit. So C0 can be anything. As long as it's not equal to 0. And then if you want to find C1, well, now you know how to find C1 from the last term. So C1 will be oops, that's a 0. That should be a 0, correct? And we get 2 times 0 plus 2, C sub 0. So this ends up being minus 7/6 C0. You can plug in and find the other values, which I had a piece of paper here somewhere where I did it. I've got so much paper laying around my world right now. It's truly frightening. All right, so you're not hanging around where you're easy to find. That's a bummer. C2, if you plug that in and compute this, it will be 21 over 40 C0. And if you plug in and compute C sub 3 will be minus 11 over 80 C sub 0. So what's your solution look like? I will show you. Remember, we assumed that our series had this specific form. Which using powers of exponents can be factored that way. And now if you want to, and this is usually how you'll see the answer given in the back of the book, C0 plus minus 7/6 C0x plus 21 over 40 C0x squared minus 11 over 80 C0x cubed. And yes, you can factor the C0 out if you want to. So there's your first series solution to that differential equation. And remember, where are those C's coming from? That was coming from our recurrence relation. So there was one of our two series if r equals 1/2. If r equals 0, then your recurrence relation becomes, here's the recurrence relation. So you'll plug 0 in for the r here, and the recurrence relation will be C sub k plus 1 equals minus k plus 3 C sub k over, let's see, what are we going to get down there? K plus 1, 2k plus 1. And you can compute your values of the constants in terms of the initial term, C naught. And from there, you get your solution, which is, remember, you assumed that you had a series solution. Here R is 0. And we'll just have C naught minus 3 C naught x plus 2 C naught x squared plus minus 2/3 C naught x cubed, and so on. And you have completed the problem. Yay! So that is the method of Frobenius. It's a lot like section 6.2. You're really not doing a ton of calculus here. You're not doing a ton of crazy stuff, but what you are doing is some advanced algebra where you've got multiple unknowns and things, and you've really got to keep your feet underneath you. And I try and do as little of this in my head because you just fry your brain cells. So there you go.